Picture our solar system for a moment, the familiar planets orbiting our sun, Earth suspended in that vast darkness. Now pull back further until our entire solar system shrinks to a single, faint speck of light. And further still, until even that speck vanishes into an ocean of stars. Out there, in that unimaginable expanse, are worlds so strange they challenge everything we thought we knew about planets. We've discovered thousands of these distant exoplanets, and some are so bizarre, so breathtakingly unexpected, that they seem ripped from the pages of science fiction. These aren't just rocky spheres or gas giants, they're planets where it rains glass sideways, worlds with two suns in their sky, orbs darker than coal, and oceans so deep they could swallow our entire solar system. What you're about to witness isn't just a tour of oddball planets, it's a journey to the very edges of possibility. Each of these 25 strange planets tells a story not just about alien landscapes, but about the stunning creativity of the cosmos itself. We're talking about planets where a year lasts only hours, where diamonds fall like hail, and where hyperviolent winds tear across surfaces hotter than some stars. These discoveries haven't just expanded our catalogue of worlds, they've rewritten the rules of planetary science, forcing us to rethink what's even possible out there in the dark. So come with us as we explore these marvels, not as distant points of light, but as real places, each with its own secrets, its own beauty, and its own lesson about how strange and wonderful the universe truly is. This is more than a countdown, it's an invitation to witness the extraordinary, and to remember that we live in a cosmos far more imaginative than we ever dreamed. Our journey into the bizarre begins not in some distant, forgotten corner of the galaxy, but remarkably close by in cosmic terms, with a world that presents a beautiful facade hiding a truly hellish reality. Meet HD 189,733b, a planet that from a great distance appears as a serene, deep blue marble, not unlike our own Earth seen from space. But this tranquil appearance is the universe's most deceptive lie. This is not a world of water and life, but a gas giant orbiting so close to its host star that its year is shorter than an Earth day, a blistering 2.2 Earth days to be exact. It is tidally locked, meaning one side is forever scorched by the star's fury while the other is trapped in endless night. This proximity creates an environment of almost unimaginable violence. The temperature difference between the day and night sides fuels hyper-hurricane winds, screaming across the atmosphere at an astonishing 5,400 miles per hour. That's over 7 times the speed of sound, a force that doesn't just howl, it shreds and scours anything in its path. And within this superheated, tempestuous atmosphere, silicate particles condense into clouds. But this isn't gentle dust, it's molten glass. These tiny shards are caught in the supersonic winds, whipping across the sky horizontally in a perpetual, blistering storm of razored glass. Imagine a hurricane where the rain isn't water, but scorching, liquid rock that solidifies into billions of flying daggers. Scientists discovered this blue beast using the transit method, where a planet is detected by the faint, rhythmic dimming of its star's light as it passes in front. But the real magic was in determining its haunting color, by measuring the precise change in light before, during, and after it disappeared behind its star. Astronomers could analyze the spectrum of light reflected off its terrifying atmosphere. They weren't looking at a picture, they were reading the light signature, and it told a story of a cobalt blue world. That iconic color comes from the very thing that makes it so deadly. Those high-altitude silicate clouds rich in magnesium silicate, essentially molten glass, that scatter blue light across the cosmos, a beautiful warning sign for a planet that is anything but hospitable. Yet the true allure of this world isn't its scorching orbit, but what lies beneath that fiery exterior. The intense pressure within its interior, a staggering force far greater than anything on Earth, is thought to crush that carbon into a crystalline structure. Theoretical models suggest that a significant portion of this planet's interior isn't just carbon. It's a vast, seething mantle of solid diamond, possibly hundreds of miles thick. We're not talking about a few precious gems scattered in the rock. We're talking about geological formations on an unimaginable scale, entire mountain ranges that might literally be made of diamond. This leads to a truly surreal possibility. With surface temperatures hot enough to melt iron and a crust potentially made of graphite, it might actually rain diamonds in the crushing depths of its atmosphere, solidifying as they fall into that glittering, indestructible interior. The story of its discovery is just as compelling as the planet itself. Astronomers found 55 Cancri E using the radial velocity method, detecting the subtle wobble its gravity induces in its home star. But to truly understand its diamond nature, they needed to know its size and mass. By also observing the planet transit or cross in front of the star, they could calculate its radius. Combining this with its mass revealed an astonishingly high density, a density that only makes sense if the planet is overwhelmingly composed of heavy elements, with carbon being the prime candidate. It's a world that challenges our very definition of value, a testament to the fact that in the cosmos, a planet made of the universe's most sought-after gemstone can be a terrifying and inhospitable place. If HD 189,733b is a beautiful lie and 55 Cancri E a glittering paradox, then our next destination is a world of pure, unadulterated shadow. Imagine a gas giant larger than our own Jupiter orbiting its star. You'd expect it to reflect a fair amount of light, much like Jupiter does in our own solar system. But TRES-2b defies every expectation. This planet is the darkest world ever discovered, a pitch-black orb darker than charcoal, darker than black acrylic paint, even darker than a freshly paved asphalt road on a moonless night. It reflects less than 1% of the light that hits it, making it essentially a black hole in appearance, a void against the starry backdrop, only revealing its presence by the light it steals. So what creates a world of such profound darkness? The secret lies in its searing atmosphere and bizarre chemical composition. TRES-2b is what astronomers call a hot Jupiter, orbiting its star at a mere 3 million miles. That's 20 times closer than Mercury is to our Sun. This intimate dance subjects the planet to blistering temperatures soaring above 1,800 degrees Fahrenheit. At that kind of extreme heat, something crucial is missing from its atmosphere: clouds. On a typical gas giant like Jupiter, bright, reflective ammonia clouds act like a giant mirror, bouncing a significant amount of stellar light back into space. But the intense heat on TRES-2b prevents these reflective clouds from ever forming, leaving its atmosphere clear and exposed, and that exposed atmosphere is a brew of nightmare chemicals. Scientists believe it's saturated with vaporized sodium and potassium, and gaseous titanium oxide, all of which are incredibly efficient at absorbing visible light. Think of it less like an atmosphere and more like a colossal cosmic sponge for photons. Incoming light doesn't stand a chance. It's swallowed whole by these light-hungry elements. What little light isn't immediately absorbed is converted into infrared radiation, glowing with a faint, dim red heat like a faraway ember, invisible to the human eye. This combination, a complete lack of reflective clouds and an atmosphere gorged on light-absorbing chemicals, creates the perfect conditions for an abyss, a planet that is quite literally the definition of nothing to see here. Confirming the existence of a world this dark was a masterclass in astronomical detective work. The Kepler Space Telescope, designed to hunt for planets by the dip in starlight they cause when transiting, was the key instrument. But for TRES-2b, astronomers also measured the even more subtle change in light that occurred when the planet, hidden from view, orbited behind its star. This secondary measurement, called an occultation, told them how much light the planet itself was reflecting. The drop was almost negligible. It was the definitive proof that they weren't looking at a dim world, but an extraordinarily dark one, a gas giant that absorbs almost all light that dares to touch it, a haunting silhouette forever circling its sun. Just when you thought the cosmos couldn't get any more contradictory, we arrive at a world that defies the most fundamental laws of common sense. Welcome to Gliese 436b, a planet that shouldn't exist, a place where water is simultaneously on fire and frozen solid. Imagine a world roughly the size of Neptune, a colossal ball of gas and ice orbiting so close to its dim red sun that its surface temperature soars to a blistering 800 degrees Fahrenheit. At that heat, you'd expect a global ocean of superheated steam, a world shrouded in a scalding, vaporous atmosphere. But Gliese 436b laughs in the face of such simple expectations. Here, the water isn't steam, it isn't even liquid. Astoundingly, it's frozen into a solid state, forming a crust of what scientists call burning ice. The secret to this impossible paradox isn't magic, it's the utterly crushing force of gravity. Gliese 436b is a massive world, and its immense gravitational pull creates an atmospheric pressure so powerful it fundamentally alters the behavior of matter itself. We're talking about pressures millions of times greater than what we experience here on Earth. Under these extreme conditions, water molecules are forced into a crystalline structure that is far denser and more resilient than any ice found in your freezer. This isn't ordinary ice, this is an exotic state of matter known as Ice 7 or potentially even Ice 10. Think of it like this: on Earth, increasing heat makes water molecules vibrate faster, breaking their bonds to become a liquid and then a gas. But on Gliese 436b, the pressure is the dominant force. It acts like a celestial vise, gripping the water molecules so tightly that they simply cannot break free and float away as gas, no matter how much thermal energy is screaming through them. The heat is trying to tear the water apart while the gravitational pressure is desperately holding it together. The result is a stalemate of physics, a shell of solid water that remains frozen even as it glows with the heat of a blast furnace. This creates a truly surreal planetary architecture. Astronomers theorize that beneath a thin, scorching hydrogen-helium atmosphere lies a vast mantle of this super-dense hot ice. And at its core, the pressure may be so unimaginably intense that it has crushed the remaining material into a solid, rocky heart. The discovery of this burning ice ball was a pivotal moment in exoplanet science. It was found using the radial velocity method, its presence given away by the persistent tug it exerts on its parent star. But understanding its true nature required a deeper look. When it was later observed transiting its star, confirming its size, the scientific community was left with a startling conclusion. A planet of that mass and radius could only be explained if a significant portion of it was water, but water behaving in a way we had never before witnessed on a planetary scale. Gliese 436b stands as a powerful testament to the fact that the universe is not merely stranger than we imagine. It is often stranger than we can imagine. It teaches us that the conditions on our own familiar worlds are just one page in a much larger and more bizarre rulebook, a cosmic manual where ice can defy fire and the impossible becomes just another Tuesday. If the previous world showed us strange chemistry and impossible states of matter, then our next discovery reveals a level of cosmic violence that is almost poetic in its tragedy. Meet WASP-12b, a planet living on borrowed time, caught in a death spiral so dramatic we can actually witness its final, agonizing act. This isn't just a hot Jupiter. It's a world being actively devoured by its parent star, a celestial feast playing out over millions of years, and we have a front-row seat to the entire spectacle. The horror begins with its orbit. WASP-12b is locked in an incredibly tight embrace with its star, completing a full revolution in just over one Earth day. This proximity subjects the planet to unimaginable stellar radiation, blistering its surface to temperatures exceeding 4,000 degrees Fahrenheit. But the heat is only part of the story. The true danger comes from the star's immense gravitational pull, which creates a tidal force so powerful it has literally stretched the planet out of its natural spherical shape. WASP-12b is no longer a ball. It has been distorted into a grotesque, teardrop-shaped world, with its elongated tip perpetually pointed toward the star that is killing it. This extreme distortion is the key to its demise. The gravitational pull on the side of the planet facing the star is so much stronger than the pull on the far side that it has overcome the planet's own gravity. The result is a continuous stream of superheated atmospheric gas being pulled directly off the planet's surface. This mass transfer streams across the space between the planet and the star, forming a visible bridge of stolen material that astronomers can actually detect. We are literally seeing the planet's own atmosphere being siphoned away, siphoned off into a swirling disk of debris that is slowly feeding the star. It's a stunningly direct observation of planetary destruction. Adding to its eerie profile is its appearance. Like TRES-2b, WASP-12b possesses an incredibly low albedo, reflecting less than 0.06% of the light that hits it. This makes it one of the darkest planets known. Scientists believe its atmosphere is utterly devoid of reflective clouds and is instead choked with substances like sodium and titanium oxide that greedily absorb visible light. But its carbon-rich nature might also play a role. It's possible the atmosphere is so hot that carbon molecules form a dark, hazy soot that further contributes to its light-eating properties, making this dying world appear as a black teardrop against the glow of its star. The clock is ticking for WASP-12b in a way we can almost quantify. Based on the observed rate of mass loss, astronomers estimate this world has perhaps 10 million years left before it is completely stripped down to its barren core or entirely consumed. In the grand timeline of the universe, that's the blink of an eye. Its inevitable fate offers us a rare and sobering glimpse into the dynamic, often violent processes that shape planetary systems, reminding us that even giant worlds are not permanent fixtures in the cosmos. Leaving the gravitational fury of WASP-12b behind, we journey to a world that feels less like a cosmic battleground and more like a scene from our favorite science fiction. Welcome to Kepler-16b, a planet that for decades existed only in the realm of imagination, most famously as the desert home of Luke Skywalker. This is the real Tatooine, the first confirmed planet caught in an eternal dance around not one, but two stars, a place where you could stand on its surface and witness a breathtaking double sunset. The existence of such a world was long thought to be nearly impossible. The complex, shifting gravitational tug of war between two stars should, in theory, tear apart any nascent disk of dust and gas trying to form a planet, or violently fling a newly formed world out into the void. Kepler-16b proved those theories wonderfully wrong. It's a cold, gaseous planet roughly the size of Saturn, orbiting a binary pair consisting of a smaller, cooler orange star and a dim red dwarf. These stars themselves are locked in a tight mutual orbit, whirling around each other every 41 days, while the planet circles them both from a distance of about 65 million miles, completing its wider, stately orbit in just over 229 days. The method used to discover Kepler-16b was a brilliant piece of astronomical deduction that went far beyond simply watching for a star to dim. The Kepler telescope did observe the primary, larger star dimming at regular intervals, which was the first clue. But then, something fascinating happened. The dimming event sometimes occurred when the planet wasn't directly in front of the star it was expected to transit. The key was realizing the other star in the system was also causing eclipses. By meticulously mapping the precise timings of all these eclipses and transits, astronomers noticed slight, telltale variations. The planet's transits were shifting because the central point of gravity in the system itself was constantly moving as the two stars danced around each other. It was this complex pattern, these transit timing variations, that confirmed the planet was orbiting both stars, a celestial choreography of three bodies. What does the sky look like on this world? The two suns would appear as a brilliant, close-knit pair, with the larger star casting an orange hue and its smaller companion a deep red. Their combined light would create long, shifting shadows across the hypothetical surface of this gas giant, while the planet itself is likely a frigid, uninhabitable world without a solid surface to stand on. Its very existence is the true marvel. It proved that planets can form and persist in the chaotic environment of a binary system, dramatically expanding the potential real estate for worlds in our galaxy. Since a majority of stars in the Milky Way are found in binary or multiple systems, the discovery of Kepler-16b meant the universe might be filled with countless such worlds, each offering its own unique and spectacular views. From the mesmerizing double sunsets of a science fiction world, we plunge directly into a vision of a primordial hellscape. If Kepler-16b is a cosmic ballet, then Kepler-10b is a glimpse into the raw, violent infancy of a planet. This is not a gas giant or an ice world, but one of the very first rocky exoplanets ever confirmed a discovery that finally gave us a direct, tangible link to the terrestrial planets in our own solar system. But the familiarity ends with its composition. Kepler-10b is a super-Earth, a world with about 4.6 times the mass of our own, and it is so profoundly scorched by its star that its entire surface is believed to be a global, roiling ocean of molten lava. The source of its infernal heat is its impossibly close orbit. This planet races around its sun-like star in a breakneck 20 hours, meaning its entire year is shorter than a single Earth day. It's parked a mere 1.8 million miles from its star, over 20 times closer than Mercury is to our Sun. At that distance, the stellar radiation is relentless and unforcing, heating the dayside surface to temperatures that defy comprehension somewhere around 2,500 degrees Fahrenheit. That's hotter than the melting point of iron and nearly half as hot as the surface of our own Sun. At such extremes, rock doesn't just get soft, it liquefies completely, creating a vast, bubbling magma ocean with no solid land in sight, a perpetual, incandescent sea under a black, star-filled sky. The most astonishing revelation about this world, however, might be what it's losing. The incredible heat is literally boiling the planet's surface away. Theoretical models suggest that the molten rock on the dayside is evaporating, creating a thin but tenuous atmosphere of vaporized silicate rock and metals. And because the planet lacks a strong magnetic field to protect it from the stellar wind, this metallic vapor is being swept away from the star-facing side, pulled and blown by radiation pressure into a long, faint stream of particles trailing behind the planet in its orbit. This gives Kepler-10b a unique and haunting feature, a glowing, comet-like tail of evaporated rock. We are witnessing a world slowly disintegrating before our eyes, leaving a trail of its own destruction across the cosmos like a ghostly signature. Confirming the existence of this lava world was a landmark achievement that required two powerful space telescopes working in concert. The Kepler mission first identified it using the transit method, detecting the telltale periodic dip in its star's brightness. But to be absolutely certain this was a solid, rocky world and not a gaseous mirage, astronomers needed to measure its mass. They called upon the precise instruments of the Kepler Space Telescope to detect the subtle stellar wobble caused by the planet's gravity. The combined data, its size from the transit and its mass from the wobble, revealed an exceptionally high density, proving conclusively that Kepler-10b was a dense, rocky body, the first of its kind ever found outside our solar system. It opened the door to understanding that terrestrial planets are common, but it also showed us that their stories can be as brutal as they are beautiful. After witnessing the fiery disintegration of Kepler-10b, our journey now takes a turn into the profound and the deeply mysterious. we leave the realm of scorching rock and enter a world of immense, crushing pressure and endless water. GJ 1214b, often called a super-Earth, is a title that feels almost comically inadequate. This is not a larger version of our home. This is a water world of almost mythical proportions, a planet so saturated with H2O that it fundamentally redefines what an ocean can be. Located a mere 42 light-years away, a stone's throw in galactic terms, GJ 1214b orbits a small, dim red dwarf star. Its year is a whirlwind 1.6 Earth days, a testament to its incredibly close orbit. But the real story isn't its speed, it's what astronomers discovered when they measured its size and mass. This planet is about 2.7 times the size of Earth and nearly 6.5 times more massive. When you crunch those numbers, the resulting density is astonishingly low. It's simply not dense enough to be a rocky world like Earth, nor is it a gaseous mini Neptune. The only substance that fits the profile that explains its puffy nature is water, a lot of water. This suggests a planetary architecture that is both beautiful and terrifying. Scientists believe GJ 1214b is composed of a relatively small rocky core, perhaps similar to Earth's in size, but enveloping that core is not a thin hydrosphere like ours. Instead, it is a global ocean, but not an ocean as we know it. We're not talking about an ocean a few miles deep. The models suggest this ocean could be hundreds of miles deep, a body of water so vast it contains multiple times all the water found on Earth. The pressure at the bottom of this abyssal plain would be staggering, millions of times greater than the pressure at the bottom of our Mariana Trench. And it is here, in these lightless depths, that the true alien nature of this world reveals itself. Under such unimaginable pressure, water doesn't behave like the simple liquid or ice we know. It is forced into exotic, high-pressure states known as hot ice or supersonic ice. This isn't ice that's cold, it's ice that's simultaneously solid and scorching hot. A crystalline structure where water molecules break apart and oxygen atoms form a solid lattice while hydrogen ions flow through it like a liquid metal. This means the planet could have a solid mantle of ice covering its rocky core, despite temperatures being hundreds of degrees hot, all capped by that hundreds of miles deep liquid ocean and a thick, steamy hydrogen-helium atmosphere that acts like a crushing lid on a planetary pressure cooker. The discovery of GJ 1214b's true nature was a masterclass in atmospheric characterization. While the Hubble Space Telescope couldn't take a picture of the planet, it could analyze the starlight filtering through its atmosphere during a transit. The spectrum it gathered was featureless, a flat line that was, ironically, bursting with information. This flatness told astronomers that the atmosphere wasn't clear and thin. It was either incredibly hazy or overwhelmingly thick and dense with water vapor, preventing the light from revealing any specific chemical fingerprints. This was the final, compelling piece of evidence pointing toward a world shrouded in a perpetual, global steam bath, a hauntingly uniform sphere of mist and deep, dark water. It stands as a powerful reminder that a planet can be made of the very substance we equate with life, and yet be one of the most utterly alien and inhospitable places imaginable. If the haunting water world GJ 1214b represents a strange form of stability under pressure, then our next destination is a monument to pure, unadulterated chaos. Meet HD 80606b, a gas giant that doesn't merely orbit its star, it survives a gravitational slingshot of cosmic proportions, enduring the most extreme seasonal shifts imaginable on a planet with the most elliptical or oval-shaped path ever discovered. This world's journey is a roller coaster of epic scale. For most of its incredibly long 111-day year, it drifts lazily in the frigid outer reaches of its system, a comfortable 85 million miles from its star, a distance similar to the space between our Sun and Venus. But then its orbit yanks it inward with terrifying speed. In a frantic burst that lasts just a single 20-hour day, it screams toward its star, accelerating to a blistering close approach of just 3 million miles. To put that in perspective, that's 8 times closer than Mercury ever gets to our Sun. This isn't a graceful arc, it's a sudden, violent dive into the inferno. The result of this celestial daredevil act is a temperature swing so violent it defies belief. In the cold, distant stretches of its orbit, the planet's dayside simmers at a modest 980 degrees Fahrenheit. But as it hurtles into its closest approach, the stellar radiation intensifies by a factor of nearly 1,000. In just those few hours, the surface temperature on the dayside skyrockets to an astonishing 2,240 degrees Fahrenheit, hot enough to melt solid iron and even some forms of titanium. The planet doesn't just get warmer, it undergoes a thermal shock, a flash heating event that creates supersonic storms as the atmosphere desperately tries to redistribute this insane influx of energy. Scientists have observed this heating happen in real time, watching the planet's infrared signature explode in brightness before slowly fading as it retreats back into the cold. So what cosmic force could possibly engineer such a chaotic path? The answer lies not with the planet itself, but with a distant binary companion. HD 80606b star is not alone. It is locked in a gravitational dance with another star, located about 900 astronomical units away. Over billions of years, the subtle, persistent gravitational tug from this stellar sibling has acted like a constant, gentle nudge on the planet's orbit. This external influence, a process known as the quasi mechanism, has progressively stretched the planet's once nearly circular path into the wildly eccentric egg shape we see today. It's a stunning demonstration of how a seemingly quiet binary star system can be the puppet master for planetary pandemonium, orchestrating a relentless cycle of ice and fire that makes this world a laboratory for studying atmospheric physics under the most extreme duress. After journeying through the extremes of scorching orbits and deep oceans, we now arrive at a discovery that is not just strange but historically profound. A system that fundamentally altered our understanding of where planets can exist and how they can be found. This is the story of the first exoplanets ever confirmed by science, worlds that orbit not a living star, but its incredibly dense, rapidly spinning corpse. Welcome to the PSRB 1257+12 system, home to the legendary zombie planets. The stage for this cosmic horror story was set by a cataclysm. Billions of years ago, a massive star much larger than our Sun reached the end of its life and erupted in a supernova explosion, one of the most violent events in the universe. This titanic blast would have utterly vaporized any planets that once called this star home, shredding them into atomic dust and blasting the material across light years of space. All that remained was the star's incredibly dense, collapsed core, a city-sized object known as a pulsar. This particular pulsar, located about 2,300 light-years away in the constellation Virgo, is a rapidly spinning neutron star, a celestial lighthouse that emits beams of intense radiation from its magnetic poles. As it spins, these beams sweep across space, and from our vantage point on Earth, we detect this as a precisely timed radio pulse, arriving every 6.22 milliseconds with a regularity that rivals the most accurate atomic clocks. It was this incredible regularity that became the key to an impossible discovery. In 1992, astronomer Alexander Wolskson was meticulously studying the timing of these pulses from PSRB 1257+12. He noticed something bizarre. The pulses were not perfectly regular. They occasionally arrived a fraction of a millisecond early and sometimes a fraction late. This was not an error in the pulsar's mechanism. It was a fingerprint of an unseen dance. Wolskson realized that the subtle, rhythmic variations were caused by the gravitational tug of planets orbiting the pulsar. As the planets moved in their orbits, they would ever so slightly pull the pulsar toward and away from Earth. When it was pulled toward us, the pulses had a slightly shorter distance to travel, so they arrived early. When pulled away, the distance was longer and the pulses arrived late. This method, known as pulsar timing, is so precise it can detect a planet's influence even if it only moves the pulsar by a few meters per second. The 3 worlds he found were truly born from ashes. It's believed they are not survivors of the supernova, but second-generation planets, zombie worlds that formed from the grave. The violent explosion would have left behind a rich, swirling disk of heavy metal debris around the pulsar. From this nebula of stellar remains, a new planetary system coalesced. The planets in this system are likely unlike anything in our solar neighborhood. They could be incredibly dense, carbon-rich worlds, possibly with crusts made of crystalline diamond forged in the heart of the supernova. Or they could be barren, rocky cores of iron and silicon, all that remained after the explosion blasted away their gaseous envelopes. Their very existence is a testament to nature's ability to create life from death, building entirely new worlds from the shattered pieces of the old. The discovery of the PSRB 1257+12 system was a monumental paradigm shift. It proved that planets could exist in the most hostile environments imaginable, bathed in deadly radiation and held in the gravitational grip of a stellar remnant. It also demonstrated a powerful new method for planet hunting, one that predated the boom in exoplanet discoveries by the Kepler mission by nearly a decade. These zombie planets, the first ever found, will forever hold a sacred place in the history of astronomy, not just for being first, but for showing us that the cosmos is far more resilient, creative, and surprising than we had ever dared to dream. After traversing the graveyard of a dead star and its resurrected worlds, our search for life turns toward a far more hopeful, yet equally enigmatic discovery. We now arrive at a world that, for a brief and shining moment, captured the global imagination like no other exoplanet before it. This is Kepler 22b, a name that might not sound as dramatic as a diamond world or a lava planet, but one that carries a profound and weighty title. The first planet ever confirmed to be orbiting comfortably within the habitable zone of a sun-like star. The concept of the habitable zone, often romantically called the Goldilocks zone, is the orbital region around a star where conditions are, in theory, just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. It's the distance where the energy from the star could allow for oceans, lakes, and rivers, the fundamental prerequisite for life as we understand it. When the Kepler telescope's data revealed a world sitting perfectly in this sweet spot around its star, located 600 light-years away in the constellation Cygnus, the announcement in 2011 was met with electrifying excitement. Here at last was a candidate that wasn't a scorched wasteland or a frozen giant, but a place that could, in the most optimistic interpretation, be a cousin to our own Earth. Kepler 22b itself is a fascinating puzzle. It's classified as a super-Earth with a radius about 2.4 times that of our planet. Its year is 290 days, not too dissimilar from our own 365, and it orbits a star that is strikingly similar to our Sun, though slightly smaller and cooler. This last point is crucial because it means Kepler 22b's orbit, while smaller than Earth's, places it in a comparable position relative to its star's energy output. If you were to place Earth in that same orbit, we would likely be a frozen world. But because its star is cooler, the planet receives a similar amount of warmth, making its surface temperature, if it has an Earth-like atmosphere, a remarkably pleasant 72 degrees Fahrenheit. It's a stunning piece of cosmic balancing. Yet for all this tantalizing potential, the true nature of Kepler 22b remains one of astronomy's most compelling mysteries. The problem is one of mass. While we know its size from the transit method, its mass is still unknown because it doesn't induce a detectable wobble in its star from our vantage point. And mass is the key that unlocks a planet's identity. Without it, we are left to speculate. Is it a massive rocky planet, a true super-Earth with a solid surface that could host continents and oceans? Or is it what astronomers call a mini-Neptune, a world with a small rocky core enveloped by an impossibly deep, dense atmosphere of hydrogen and helium, beneath which any surface would be subject to pressures that would crush any hope of Earth-like conditions? Perhaps it's something in between a water world, a global ocean planet shrouded in a thick, steamy atmosphere. This fundamental uncertainty is what makes Kepler 22b so important. It is the archetype, the first of thousands of such habitable zone planets we have now discovered. It taught us that such worlds are not rare flukes but common features of our galaxy. It represents not a final answer but a magnificent beginning, a beacon that proved the search for another Earth was not a quixotic quest but a realistic scientific endeavor. It shifted the conversation from "Are there other Earths?" to "What kind of Earths are out there?" Its legacy is not in what we know about it, but in the countless worlds it inspired us to find and the relentless pursuit to understand them, reminding us that the most hopeful discoveries are often those that open the door to even greater questions. Leaving behind the hopeful mysteries of potentially habitable worlds, we now set our sights on a celestial marvel that dwarfs anything in our own solar system, a ringed giant so extravagant it makes Saturn look like an amateur. This is J1407b, a world often dubbed the Super Saturn, and that name is not the slightest bit of an exaggeration. While we marvel at Saturn's magnificent rings, they are utterly dwarfed by the colossal, staggering disk system encircling this distant planet. If Saturn's rings were a single, elegant bracelet, the rings of J1407b would be an entire city's infrastructure of highways and overpasses, a complex web of dust and ice on a scale that is almost impossible to fully comprehend. The numbers alone are enough to boggle the mind. The entire ring system of J1407b is estimated to be nearly 120 million kilometers in diameter. That's over 200 times larger than the ring system of Saturn. To put that in perspective, if you could somehow place this ring system in our own solar system, it would occupy a greater area of the sky than the Sun itself, completely engulfing the orbits of Mercury, Venus, Earth, and Mars. The planet at the center of this cosmic spectacle is itself a behemoth, most likely a gas giant many times more massive than Jupiter, though its immense size is utterly overshadowed by the sheer grandeur of its rings. These aren't just simple, uniform bands. Observations suggest a complex structure with distinct gaps, likely carved out by the gravitational influence of embedded exomoons, creating a system that resembles a gigantic phonograph record spinning around a central point. The story of its discovery is a brilliant piece of astronomical detective work that didn't involve seeing the planet or its rings directly. Instead, it was found through its shadow. Astronomers were monitoring its parent star, J1407, and in 2007 they witnessed something unprecedented. The star's light didn't just dip in a clean, symmetrical curve as a planet would cause. It flickered. It dimmed in a bizarre, complex series of fluctuations that lasted for 56 days. This wasn't the signature of a simple spherical object transiting the star. This was the unmistakable fingerprint of an incredibly complex, uneven structure, a vast system of rings with varying densities passing in front of the star and blocking its light in an intricate pattern. By meticulously analyzing this unique light curve, scientists could actually map the rough structure of the rings, identifying not only their breathtaking scale but also those telltale gaps. Those gaps are perhaps the most exciting part of the entire discovery. In Saturn's rings, gaps are cleared out by the gravitational pull of small shepherd moons. The presence of similar gaps in the rings of J1407b strongly suggests the same process is at work there, but on a titanic scale. One gap in particular is so pronounced that astronomers have calculated the object clearing it would have to be roughly the size and mass of Earth or even Mars. We are likely looking at the birth of an exomoon, a colossal new world forming within the spacious confines of its own immense circumplanetary disk. This provides us with a rare and invaluable real-time look at the processes that may have formed the moons around our own gas giants billions of years ago. J1407b is more than just a planetary oddity. It's a colossal natural laboratory, offering a snapshot of a young, dynamic system where new worlds are being sculpted from dust and ice right before our eyes. Shifting from the immense moon-forming rings of a super Saturn, we venture into the profound and utter cold of deep interstellar space, to a world that represents the absolute antithesis of a scorching lava planet. Meet Ogle 2005 BLG 390lb, a frozen super-Earth so profoundly cold that the very air we breathe would freeze solid and fall to the ground like winter hail. Located an almost unimaginable 21,500 light-years away, near the center of our Milky Way galaxy, this planet orbits a small, dim red dwarf star. Its vast distance from that faint stellar ember means it receives virtually no warmth, plunging its surface into a deep freeze with estimated temperatures hovering around -364 degrees Fahrenheit. That is only 50 degrees Fahrenheit above the coldest temperature possible in the entire universe, absolute zero. This isn't just a chilly winter day. This is a permanent, global state of cryogenic stasis, a world locked in an ice age so extreme it defies terrestrial comparison. The method used to find this icy speck is as extraordinary as the world itself, a technique that relies on one of Einstein's most famous predictions, that gravity can bend light. This process is called gravitational microlensing, and it is one of the most delicate and rare feats in all of astronomy. Here's how it works for a planet like this. Astronomers using the optical gravitational lensing experiment, or Ogle telescope, were continuously monitoring millions of stars near the galactic bulge, watching for any change in their brightness. They were waiting for a specific celestial alignment, a foreground star drifting precisely in front of a much more distant background star. When this happens, the gravity of the foreground star acts like a lens, magnifying and brightening the light from the background star for a period of weeks. This event is rare enough, but if the foreground star has a planet orbiting it, the planet's own gravity adds a tiny additional bump, a brief and secondary spike in the magnified light. It's an incredibly faint signal, a flicker within a flicker, that lasts for less than a day. Catching it requires immense patience, a global network of telescopes on constant alert, and a tremendous amount of luck. The discovery of Ogle 2005 BLG 390lb in 2005 was a landmark moment because it was one of the first times this microlensing method had been used to detect a planet with such a low mass, proving the technique could find small, rocky worlds at enormous distances. The data revealed a planet with a mass about 5.5 times that of Earth, suggesting a rocky composition, orbiting its star at a distance roughly 3 times farther than Mars is from our Sun. But because its host star is so small and dim, that great distance translates into virtually no stellar heating at all. Scientists speculate that this world is likely a barren, rocky ball sheathed in a permanently frozen atmosphere, probably composed of gases like nitrogen, oxygen, and argon that have all sunk to the surface as ice. Any volatile compounds, including water, would exist only as ancient rock-hard ice, more solid than granite. What makes this frozen super-Earth so important isn't its potential for life, but its powerful lesson in planetary diversity. For a long time, many models of planet formation suggested that small, rocky worlds like Earth would primarily be found close to their stars, while gas giants would dominate the outer, colder regions of a system, just as we see in our own solar neighborhood. Ogle 2005 BLG 390lb shatters that comfortable assumption. It proves that rocky planets can and do form or migrate to the frigid outer reaches of their stellar systems. This discovery forces us to broaden our perspective, showing that the architecture of planetary systems across the galaxy is far more varied and unpredictable than we once believed. It stands as a silent, frozen sentinel, reminding us that the cosmos is filled with every conceivable type of world, from the blistering infernos to the silent, ice-locked realms at the very edge of darkness. But if the tantalizing mystery of Kepler 22b left us yearning for a world that felt truly familiar, then our next discovery delivered in a way that sent ripples through the entire scientific community. Journey with us now to Kepler 186f, a planet that earned a title no other world had ever truly held before. The first validated Earth-sized planet discovered orbiting comfortably within the habitable zone of its star. This wasn't just another super-Earth or a gassy mini-Neptune. This was a world with a radius only 10% larger than our own, a place where the very scale of the landscape would feel hauntingly recognizable. Kepler 186f orbits a small, cool M-dwarf star located about 500 light-years away in the constellation Cygnus. This star, Kepler 186, is significantly smaller and redder than our Sun, emitting most of its energy in the infrared part of the spectrum. Because of this, its habitable zone is shifted much closer in. Kepler 186f orbits at a distance that would place it somewhere between Mercury and Venus in our own solar system, a location that would be disastrously hot around our Sun. But around this dim red star, the planet receives just the right amount of stellar energy to, in theory, allow for liquid water to pool on its surface. Its year is 130 days, a stately pace as it circles its crimson sun. The profound implication of its size cannot be overstated. A planet only slightly larger than Earth has a much stronger probability of being a rocky world with a solid surface rather than a gaseous one. It exists right at that crucial boundary where gravity is strong enough to hold onto a life-sustaining atmosphere, but not so strong that it would accumulate a massive, crushing envelope of hydrogen and helium. This combination of the right size and the right location makes it the closest analog to our own world we had found at the time of its discovery in 2014, a true evolutionary cousin in the great galactic family of planets. However, life around a red dwarf star comes with a set of extraordinary challenges, the greatest of which is likely tidal locking. Just as our moon always shows the same face to Earth, planets orbiting very close to their stars tend to become tidally locked. This means one side of Kepler 186f would be in perpetual, blistering daylight, while the other is trapped in an eternal, frigid night. The potential for life would then exist in the thin, temperate ribbon of twilight at the terminator line, the border between these two extreme hemispheres. On the day side, any water would risk boiling away, while on the night side, it would be frozen into a global glacier. But in that golden middle, conditions could be just stable enough for liquid water to persist. The nature of its atmosphere is the great unknown that will define its true character. Does it have a thick, insulating blanket of gases like Venus that could efficiently redistribute heat from the day side to the night side, mitigating the extremes of tidal locking? Or is its atmosphere thin and tenuous like Mars, leaving the surface exposed to the harshness of its environment? The color of its sky is another captivating mystery. Because its star emits predominantly red and infrared light, the photosynthesis that might evolve on such a world would be adapted to these wavelengths, potentially leading to vegetation with colors far different from Earth's green. Think shades of black or deep purple to absorb every available photon. The very light that bathes the landscape would be a dim, perpetual sunset glow, a romantic yet eerie hue. Kepler 186f stands as a powerful symbol in the search for life, not because we know it is habitable, but because it proved that planets with the potential for Earth-like conditions are not rare flukes. It expanded our definition of a habitable world and cemented the idea that our pale blue dot is almost certainly not alone. Yet for all the profound cold and hopeful Earth-like scales we've encountered, the universe is always ready to reintroduce us to pure, unadulterated extravagance. Our next destination is a world that seems to have been designed by a celestial jeweler, a place where the very clouds in the sky are made of precious gems. Welcome to HTP 7b, an ultra-hot Jupiter where the atmosphere doesn't just conduct weather. It conducts a spectacular light show of crystallized minerals, potentially creating clouds of vaporized corundum, the very mineral that forms rubies and sapphires on Earth. This planet is the definition of extreme. It orbits so close to its host star that its year is a frantic 2.2 Earth days, and its dayside surface temperature is a furnace like 4,200 degrees Fahrenheit hotter than some stars. At such staggering heat, the elements that would form rocks on a cooler world are instead vaporized, existing as gaseous components in a scorching, turbulent atmosphere. Aluminum and oxygen, two of the most common elements in planetary crusts, become suspended in this superheated air. Under the right conditions of temperature and pressure, these elements can condense out of the atmospheric soup, not as simple dust but as microscopic crystals of corundum. The idea of gemstone clouds is not just poetic speculation. It is a serious scientific model born from the need to explain this planet's bizarre behavior. Astronomers first got a hint of HTP 7b's unusual nature from the Kepler Space Telescope, which observed its transit. But the real breakthrough came from studying not just the amount of light coming from the star system, but the specific quality of that light. A team of astronomers used a technique called polarimetry to analyze the light reflected off the planet's atmosphere. As light waves travel through space, they normally vibrate in all directions. However, when light is reflected off certain types of surfaces or scattered through specific types of particles, those waves can become aligned or polarized. This polarization carries a unique signature, a hidden message about what it bounced off of. The data from HTP 7b revealed a polarized light signal that was dynamic and shifting over time. This was the critical clue. It pointed to the presence of clouds, not static features, but changing weather patterns in the upper atmosphere. But simple water vapor or ammonia clouds would have vaporized instantly at such temperatures. The only substances that could both condense into clouds at that extreme heat and also be highly reflective were exotic compounds like corundum. These tiny corundum particles would scatter the blue light from the star, potentially giving the planet's atmosphere a brilliant azure or violet hue, while also creating that telltale polarized glare. The weather on this world is as violent as it is beautiful. The planet is tidally locked with a permanent day side facing the star and a permanent night side in darkness. The intense heat on the day side creates powerful winds that scream towards the night side, where temperatures are slightly cooler. It is in this transition zone on the planet's western terminator, the boundary between day and night, that scientists believe these glittering clouds form, much like clouds form on Earth when warm, moist air rises and cools. On HTP 7b, the condensing material isn't water, it's vaporized mineral. These clouds are then thought to precipitate, but there is no gentle rain here. At these temperatures, the corundum droplets would likely fall as a shower of liquid sapphire and ruby before vaporizing again, long before they could ever reach any hypothetical surface, caught in an endless, dazzling cycle of creation and destruction. This world stands as a stunning reminder that the laws of physics and chemistry can create beauty of the highest order, even in the most violent and inhospitable corners of the cosmos. If HTP 7b is a world of glittering mineral clouds, then Kelt 9b is a realm of pure, unadulterated stellar fury, a place where the very concept of a planet is pushed to its absolute breaking point. This isn't just a hot world, this is the hottest planet ever discovered, a title it holds with such absolute authority that its very existence seems to defy logic. Imagine a gas giant larger and more massive than Jupiter, but instead of orbiting at a safe distance, it is skimming the surface of its host star, so close that its year is a frantic 1.5 Earth days. This proximity subjects it to a blistering, relentless onslaught of radiation, heating its day side to an almost incomprehensible 7,800 degrees Fahrenheit. To grasp that number, consider this: that is hotter than the surface of 90% of all the stars in our galaxy, including some red dwarfs. This is not a planet being warmed by a star. This is a planet being roasted alive. The view from this world's tortured surface, if one could ever exist, would be both magnificent and terrifying. Its host star, Kelt 9, is a blue type of star, a breed that is significantly larger, hotter, and brighter than our own sun. Because the planet orbits so incredibly close, this star would not appear as a distant disk in the sky. It would dominate the entire heavens, looming a staggering 70 times larger than our sun appears from Earth. It would be an all-encompassing wall of incandescent blue-white fire, filling the sky from horizon to horizon with a light so intense it would be utterly blinding. There would be no night, no reprieve, only a perpetual, scorching day under a celestial forge. At these mind-bending temperatures, matter behaves in ways we would never see on any other world. The immense heat on the day side provides atoms with so much energy that molecules simply cannot hold themselves together. On a cooler gas giant like Jupiter, the atmosphere is filled with stable molecules like molecular hydrogen and water vapor. But on Kelt 9b, those molecules are violently torn apart into their constituent atoms. Even incredibly sturdy molecules like titanium oxide and iron, which can exist in the atmospheres of other hot Jupiters, are ruthlessly dissociated here. The dayside atmosphere is therefore a seething soup of individual atoms, a plasma of hydrogen, helium, and vaporized heavy metals, all swirling in a superheated chaos. This planetary disintegration doesn't stop with the atmosphere. The extreme heat is literally boiling the planet away. Much like WASP-12b, Kelt 9b is losing mass at a phenomenal rate, with its evaporating atmosphere being stripped away by the stellar wind and forming a vast, comet-like tail of lost material that stretches out behind it in its orbit. Scientists estimate it is losing hundreds of millions of tons of mass every second, a testament to the incredible violence of its environment. The planet is caught in a fight it cannot win, being slowly but surely vaporized by its own sun. Its discovery, made by the Kilodegree Extremely Little Telescope survey, was a shock to astronomers. It proved that planets can form and persist, at least temporarily, around the most violent and short-lived types of stars in the universe, expanding our understanding of planetary resilience to the absolute limit. Kelt 9b is a brief, brilliant candle burning at both ends, a stunning example of a world living on the very edge of oblivion. Yet even the incandescent fury of Kelt 9b represents a phase in a star's life, a brilliant but fleeting youth. For a truly enduring possibility of life, we must look to stars that offer stability over billions of years, to planets that have had the one thing our own Earth has had in abundance: time. This brings us to a world that, upon its discovery, was heralded with a profound and stirring title: Earth's bigger, older cousin. This is Kepler 452b, a planet that doesn't just resemble our own in a few key metrics. It presents a compelling vision of what our own world might one day become, given the deep, slow passage of cosmic time. Located roughly 1,400 light-years away in the constellation Cygnus, Kepler 452b orbits a star that is a veritable twin of our Sun. Known as a G-type main sequence star, Kepler 452 is almost identical to our Sun in both size and temperature, differing by only a marginal 4% in mass and a 10% increase in diameter. It shares the same spectral classification, meaning it emits the same familiar yellow-white light that has nurtured life on our planet for eons. This is a crucial distinction from many other habitable zone planets that orbit smaller, cooler, and more volatile red dwarf stars. Around Kepler 452, the daylight would look familiar, and the rhythms of energy received by the planet would be strikingly similar to those on Earth. The planet itself completes an orbit every 385 days, a year length that is astonishingly close to our own 365. It resides firmly within its star's habitable zone, that Goldilocks region where temperatures could allow for liquid water to exist on the surface. But the most captivating statistic of all is its age. The Kepler 452 system is estimated to be about 6 billion years old. That makes it roughly 1.6 billion years older than our own solar system. This immense span of time is the source of the planet's most tantalizing possibilities and its most haunting questions. What does an extra 1.6 billion years of cosmic evolution potentially mean? For a planet that may have started with Earth-like conditions, it represents an almost unimaginable head start. It is a duration longer than the entire time it took for life on Earth to progress from the first single-celled organisms in the primordial soup to the technological civilization we have today. If the ingredients for life were present on Kepler 452b, water, a suitable atmosphere, and the right chemical building blocks, there has been an enormous expanse of time for biology to not only begin but to evolve, complexify, and potentially achieve sentience. The sheer possibility inherent in that additional time is enough to fuel the imagination, suggesting a world where life, if it exists, could be far more ancient and advanced than anything we know. Of course, this extended timeline is a double-edged sword. With great age comes great change, and the planet's increased size, it's about 60% larger in diameter than Earth, plays a critical role in its potential story. That larger size likely means stronger surface gravity, which would have helped it retain its atmosphere more effectively over billions of years. However, as a star ages, it gradually grows brighter and hotter. Our own sun has increased in luminosity by about 30% since its birth, and in another billion years, it will likely render Earth too hot for most life. The star Kepler 452, being older, is now about 20% brighter than it was in its youth. This suggests the planet may be experiencing a powerful greenhouse effect, potentially undergoing a runaway warming cycle similar to the one that turned Venus into a scorching hellscape. The older, bigger cousin we see today might not be a lush, thriving world, but a preview of Earth's own distant future, a warmer, perhaps drier planet where the oceans are slowly steaming away into space. This fundamental uncertainty is what makes Kepler 452b such a poignant and important discovery. It is a mirror held up to our own world, reflecting not just what is, but what could be, given the relentless forward march of time. It represents a single data point in the vast experiment of cosmic evolution, a testament to the fact that planets and their stars are not static portraits but dynamic, evolving systems. Whether it is a verdant, ancient biosphere or a warning of things to come, Kepler 452b stands as a powerful symbol in our quest, reminding us that to find another Earth is also to inevitably confront the future of our own. After gazing upon the potential future of our own world with Kepler 452b, we now turn to a discovery that feels like a glimpse into a planetary crime scene, a world that presents a profound and violent mystery. Meet TOI 849b, a planet that should not exist. Located 730 light-years away, this world was found orbiting perilously close to a sun-like star, completing a full revolution in a blistering 18 hours. But its orbit isn't the shock its very composition is. This is a planet that has been stripped bare, a colossal naked core floating in the void, offering astronomers an unprecedented look at the heart of a giant. The first clue to its bizarre nature came from NASA's TESS mission, which detected its transit and revealed its size. TOI 849b is roughly 3.4 times wider than Earth, making it about the size of Neptune. But when astronomers used the HARPS instrument in Chile to measure its mass, they got a staggering result. This Neptune-sized planet weighs over 40 times the mass of Earth. The density calculated from these figures was off the charts, nearly twice that of Earth and 5 times denser than Neptune. A planet of that size should be a gaseous world, puffy and light. TOI 849b is incredibly dense, a bloated ball of rock and metal. The inescapable conclusion is that we are not looking at a typical planet. We are looking at the exposed, solid core of a gas giant, a planetary interior that has been violently denuded of its massive gaseous envelope. The question immediately becomes, what catastrophic event could have possibly ripped away an entire atmosphere of that scale? Scientists have 2 leading theories, each more dramatic than the last. The first is a story of slow, relentless erosion. The planet orbits so close to its star that it is bathed in intense ultraviolet radiation. This could have superheated the outer layers of its original atmosphere, causing it to puff up and evaporate over billions of years, with the stellar wind steadily blowing the escaping gas away into space. It's a planetary version of death by 1,000 cuts, a slow and systematic stripping away of its identity. The second theory is far more violent and immediate. It's possible TOI 849b suffered a cataclysmic collision early in its life, a direct impact with another protoplanet so colossal that it literally blasted the entire gaseous shell into oblivion in a single apocalyptic event. Alternatively, its current orbit might not be its birthplace. It could have migrated inward from the cold outer regions of its system, coming too close to the star and experiencing tidal forces so extreme that they ripped its atmosphere away in a singular, traumatic episode. What makes TOI 849b so uniquely valuable to science is that it provides a direct, hands-on look at something we could previously only model through theory, the core of a gas giant. By studying its composition, we can finally understand what the centers of planets like Jupiter and Saturn are truly made of, solving mysteries about their formation and internal structure that have persisted for decades. It is a horrific and beautiful accident of cosmic violence, a planetary fossil that tells a story of destruction while simultaneously revealing the deepest secrets of planetary birth. If the stripped-down core of TOI 849b represents a planetary tragedy, then our next discovery is a story of pure, unadulterated chaos, a gas giant that doesn't follow a stately circular path, but instead rides a gravitational roller coaster of epic proportions. This is HR 5183b, a world astronomers have nicknamed the Whiplash Planet, and its orbit is so wildly eccentric it looks less like a circle and more like a cigar, a stretched-out ellipse that takes it on a journey of extreme climatic swings. Most planets in our solar system, and indeed most we've found elsewhere, orbit their stars in paths that are nearly circular. This provides a stable, predictable environment. HR 5183b throws that rulebook out the window. Its orbit is incredibly elongated. For the vast majority of its long, 74-year orbit, this planet is a recluse, drifting lazily in the cold outer reaches of its system, about as far from its star as Jupiter is from our Sun. Out there, it's a frigid world, but then its path yanks it inward with terrifying speed. It doesn't gently spiral closer. It screams toward its star in a dramatic dive that brings it breathtakingly close, swinging inside the orbit of Mars in our own solar system before being flung back out into the deep freeze. This isn't a gentle seasonal change. It's a dramatic, violent whiplash between two extremes. The effect on this world, were it to have any moons or a surface to stand on, would be apocalyptic. The temperature swing would be staggering, shifting by hundreds of degrees over a relatively short period. Any atmosphere would be subjected to incredible stress, potentially leading to cataclysmic storms as it desperately tries to redistribute the sudden influx of stellar heat. The changing gravitational pull from the star at such a close approach would also create immense tidal forces, flexing and heating the planet's interior in a relentless geological massage. It's a world living a life of prolonged, quiet deep freeze punctuated by brief, terrifying bursts of stellar inferno. So what could possibly cause such a bizarre and unstable path? Astronomers have a compelling suspect, a gravitational crime committed in the system's past. The leading theory is that HR 5183b wasn't always alone. It likely once had a sibling, another massive gas giant sharing its system. The two giants would have gravitationally jostled each other for dominance, and eventually they came too close. In a gravitational game of chicken, one planet was violently flung out of the system entirely, becoming a rogue planet drifting forever in the darkness between stars. The other, HR 5183b, paid a different price. The encounter transferred a massive amount of energy, slingshotting it into the incredibly eccentric orbit we see today. It's the survivor of a planetary duel, left with a permanent scar in the form of its chaotic path. This discovery profoundly challenges our models of how planetary systems form and evolve. We once thought solar systems were generally calm, orderly places where planets settled into stable, nearly circular orbits over billions of years. HR 5183b is direct evidence that sometimes the opposite is true. Systems can be violent and chaotic, with gravitational interactions dramatically reshaping orbits long after the planets have formed. It forces us to consider that our own solar system, with its well-behaved planets, might be the exception rather than the rule, and that these cosmic bad boys, these eccentric Jupiters, might be far more common than we ever imagined. Following the gravitational roller coaster of HR 5183b, our search for stability and potential life brings us to a world that stands as a fortress of rock in the habitable zone, a place where the promise of Earth-like conditions meets the harsh reality of a red dwarf environment. Meet LHS 1140b, a super-Earth that has quickly become one of the most compelling targets in the entire search for life beyond our solar system. Unlike many exoplanets that present a list of tantalizing maybes, this world offers a set of concrete, encouraging facts that make astronomers genuinely optimistic. Located a relatively close 49 light-years away in the constellation Cetus, LHS 1140b orbits a small, dim red dwarf star. These M-dwarf stars are the most common type in our galaxy, but they are notoriously tempestuous, often prone to erupting with violent flares that can sterilize the surfaces of any orbiting planets with blasts of X-ray and ultraviolet radiation. What makes LHS 1140b so special is that it appears to be a remarkable exception to this rule. Its host star is unusually quiet and stable for its class, a calm parent that offers its planetary child a far more peaceful existence than the chaotic upbringing most red dwarf planets endure. The planet itself is a dense, rocky titan with a mass about 6.5 times that of Earth and a diameter only 1.7 times larger. When you combine those two measurements, the resulting density tells a story of a world that is almost certainly terrestrial, a rocky super-Earth with a solid iron core and a rocky mantle, not a gaseous mini-Neptune. It's the kind of world you could theoretically stand on, albeit under a gravity about 3 times stronger than what we experience here. But the most critical piece of data is its orbit. LHS 1140b resides squarely in the middle of its star's habitable zone, that cherished region where temperatures could allow for liquid water to exist on the surface. However, orbiting this close to a red dwarf star comes with a significant catch: tidal locking. Just as our moon always shows one face to Earth, LHS 1140b is almost certainly locked, with one hemisphere in permanent, blistering daylight and the other in eternal, frigid night. For decades, this was considered a death knell for habitability. creating a world of extremes with a narrow, potentially uninhabitable twilight zone in between. But new research has dramatically revised this pessimistic view. The planet's substantial mass and density suggest it could have held onto a thick atmosphere over billions of years. A robust atmosphere would act like a global heating blanket, efficiently circulating warmth from the scorching day side to the frozen night side, potentially creating large regions with temperate, life-friendly conditions instead of two brutally opposed hemispheres. Furthermore, scientists have begun to speculate about another breathtaking possibility. The planet's high density could be explained if it has a composition rich in minerals that hold water. Some leading models propose that LHS 1140b might not just have an ocean on its surface, it could be a true water world, with a global ocean dozens of miles deep enveloping the entire planet. If this is the case, the combination of a deep ocean and a thick atmosphere would be a powerful recipe for climate stabilization, making the surface environment remarkably stable and potentially habitable across a wide area. This world is no fragile, airless rock. It is a planetary bulldozer, a heavyweight champion with the sheer gravitational muscle to potentially build and maintain a welcoming environment against the odds. The next generation of telescopes, particularly the James Webb Space Telescope, has LHS 1140b at the very top of its observation list. Its calm star, large size, and favorable orbit make it a perfect laboratory for atmospheric spectroscopy. By analyzing the starlight that filters through the planet's atmosphere during a transit, Webb will be able to search for the chemical fingerprints of water vapor, methane, oxygen, and even artificial pollutants biosignatures that could hint at the presence of a biosphere. LHS 1140b represents a new chapter in exoplanet science, moving from mere discovery to detailed characterization. It's a world that invites us not just to find it, but to truly understand it, offering our best chance yet to peer across the light years and finally answer the ancient question, are we alone? But if you thought gemstone clouds or disintegrating atmospheres were the limit of planetary weather, prepare to witness a storm of truly biblical proportions. Our journey now takes us to WASP 76b, an ultra-hot Jupiter where the forecast is eternally, horrifyingly simple, scorching clear skies with a 100% chance of raining molten iron. This is a world where the very elements of industry and construction are vaporized on one side of the planet, only to condense and plummet from the sky on the other in a perpetual metallic deluge. Located about 640 light-years away in the constellation Pisces, WASP 76b is the archetype of an ultra-hot Jupiter, a class of planets defined by their sheer, incinerating proximity to their stars. It orbits its host star so closely that its year is a frantic 1.8 Earth days, and it is tidally locked. This means one side of the planet, the day side, is permanently facing the stellar furnace, while the other is condemned to an endless frigid night. The temperature difference this creates is the engine for its hellish weather. The day side is heated to an almost inconceivable 4,400 degrees Fahrenheit. At that extreme heat, metals like iron don't just melt, they vaporize, turning into a gaseous component of the superheated atmosphere. Atoms are ripped apart with so much energy that molecules cannot form, creating a seething, elemental soup. The magic and the horror happens at the terminator, the razor-thin border between eternal day and eternal night. On the day side, powerful winds carry this iron vapor from the hotter regions toward the slightly cooler limb of the planet. As this metal-rich air crosses over into the darkness of the night side, where temperatures plummet by nearly 1,000 degrees, it encounters a sudden and drastic chill. The iron vapor can no longer remain in a gaseous state. It condenses first into a mist of tiny droplets, then coalescing into larger globs of molten metal that plummet from the sky. Imagine standing on the night-side surface of this gas giant, though there is no surface to stand on, looking up into a black, starless sky and seeing not water, but incandescent droplets of liquid iron streaking downward like a shower of blazing meteors. The discovery of this incredible phenomenon was a landmark achievement in exoplanet atmospheric science, made possible by a technique called high-resolution spectroscopy. A team of astronomers using the espresso instrument on the Very Large Telescope in Chile didn't take a picture of the planet. Instead, they performed a chemical analysis of its light. As WASP-76b transited its star, starlight filtered through the thin sliver of its atmosphere on the planet's leading and trailing limbs. By breaking this filtered light into an incredibly detailed spectrum, scientists could identify the unique chemical fingerprints of specific elements present in the air. They detected the clear, strong signature of iron vapor at the evening terminator, the boundary where the day side rotates into night. But when they looked at the morning terminator, where the night side rotates into day, that iron signature was gone. The iron was present on one side of the planet and absent on the other. The only logical explanation was that the iron was condensing out of the atmosphere on the night side and falling as rain, leaving the morning atmosphere devoid of its vapor. This was not inference or theory. It was direct observational evidence of precipitation on an alien world, a stunning confirmation of a weather cycle far more extreme than anything found in our own solar system. WASP-76b stands as a brutal and beautiful testament to the raw power of planetary physics, a place where the universe demonstrates its ability to forge even the most familiar elements into terrifyingly unfamiliar storms. Yet after the incandescent fury of metallic storms and stripped bare cores, our quest for another Earth brings us to a discovery that feels like a moment of cosmic serendipity, a world that was hiding in plain sight until human curiosity and a meticulous eye unearthed it from a mountain of old data. This is Kepler 1649c, an exoplanet that, on paper, presents the most compelling statistical profile of an Earth twin we have ever found beyond our solar system. It is a rocky world almost exactly our size, orbiting squarely within the habitable zone of its star, a combination of key Earth-like characteristics that no other known exoplanet has matched so precisely. The story of its discovery is a testament to the enduring value of scientific data and the power of human diligence. The Kepler Space Telescope, during its primary mission, collected light curves from hundreds of thousands of stars, generating a dataset so enormous that automated computer algorithms were tasked with the first pass to identify the telltale dips signaling a potential planet. These algorithms are incredibly powerful, but they are not perfect. In 2020, a team of scientists and a dedicated group of citizen scientists working with the Kepler False Positive Working Group decided to take a second look through the archives, manually reviewing thousands of signals that the algorithms had previously discarded as likely glitches or noise. It was in this digital haystack that they found the needle, a faint but persistent signal from a star called Kepler 1649, located 300 light-years away in the constellation Cygnus. A signal the robots had missed. The reanalysis revealed not one, but two planets, and the outer one, Kepler 1649c, was the jewel. The numbers that emerged were nothing short of stunning. Kepler 1649c is a mere 1.06 times the size of Earth, making it virtually identical in scale to our own planet. This dramatically increases the probability that it is a rocky world with a solid surface rather than a gaseous one. It orbits its host star, a small and cool red dwarf, every 19.5 Earth days. While that may seem incredibly fast because the star is so much dimmer and cooler than our Sun, this short orbital period actually places the planet perfectly within the star's conservative habitable zone. The estimated amount of stellar energy it receives from its Sun is 75% of what Earth receives from our Sun, a value remarkably close to our own, suggesting that its equilibrium temperature could be very similar to Earth's, assuming a comparable atmosphere. This combination of the right size and the right temperature is what sets Kepler 1649c apart from other promising candidates like TRAPPIST-1e or Proxima Centauri b. While those worlds are also Earth-sized and in their habitable zones, Kepler 1649c's stellar flux is the closest match to Earth's we have found. It exists in that Goldilocks sweet spot where liquid water could readily exist on its surface without boiling away or freezing solid. Furthermore, the system itself shows an intriguing hint of stability. The other planet in the system, Kepler 1649b, is a hot, rocky world orbiting closer in, and the two planets appear to be in an exact orbital resonance, with the inner planet completing 9 orbits for every 4 of Kepler 1649c. Such precise, stable resonances often indicate a planetary system that has settled into a long-lived, peaceful configuration, a positive sign for the persistence of any potential environment over billions of years. Of course, the red dwarf environment presents its now familiar challenges. The planet is likely tidally locked with a permanent day side and night side. The star, while relatively quiet compared to some flaring red dwarfs, still poses a threat from stellar eruptions that could strip atmospheres and bombard the surface with harmful radiation. The true potential of this world hinges on a question we cannot yet answer. Does it have a protective magnetic field and a sufficiently thick atmosphere to mitigate these harsh conditions? A robust atmosphere could circulate heat from the day side to the night side, creating a wide range of temperate climates, and could also act as a shield against radiation. The next generation of telescopes will be tasked with hunting for those atmospheric clues. Kepler 1649c is not a confirmed second Earth. It is the most Earth-like promise we have yet discovered, a beacon of hope that somewhere in the darkness, a world with our scale and our temperature is waiting, encouraging us to keep looking, to keep questioning, and to never stop searching the archives of both space and data for the next great discovery. But if the Earth-like promise of Kepler 1649c represents a familiar path toward life, our next discovery dares us to imagine an entirely different, far stranger cradle for biology. We now arrive at a world that single-handedly invented a new category of planet, one that could potentially host life in an environment utterly alien to our own. This is K218b, a mysterious mini-Neptune that has become the epicenter of one of the most thrilling and controversial debates in modern astronomy, all because of a single revolutionary discovery, the undeniable signature of water vapor in its atmosphere. Located 120 light-years away in the constellation Leo, K218b orbits a cool, dim red dwarf star within its habitable zone. For years, this planet was catalogued as an interesting but ultimately uninhabitable mini-Neptune, a world larger than Earth but smaller than Neptune, likely shrouded in a thick, crushing envelope of hydrogen and helium gas, with any surface buried under pressures that would instantly obliterate any known form of life. It's about 2.6 times the size of Earth and nearly 8.6 times more massive, placing it squarely in a size category where most planets are gassy, not rocky. The traditional view held that such worlds were fascinating to study but were not candidates in the search for life. That all changed in 2019. Using the Hubble Space Telescope, astronomers performed a meticulous analysis of the starlight that filtered through K218b's atmosphere during several transits. When they broke that light down into its constituent colors, creating a spectrum, they found the unmistakable fingerprint of water vapor. This was a monumental detection. It was the first time water vapor had ever been identified in the atmosphere of a habitable zone planet outside our solar system. But this discovery raised a far more profound question than it answered. What kind of world is this exactly? The answer may be an entirely new class of planet for which scientists have coined the term Haitian world, a portmanteau of hydrogen and ocean. the Hycean world hypothesis dares to reimagine the potential for life on these larger, gaseous planets. The model suggests that beneath a primary atmosphere dominated by hydrogen, which is much lighter and less oppressive than previously assumed, there could exist a planet-wide ocean. This wouldn't be an ocean sitting on a rocky seabed like Earth's. It could be a global water layer hundreds of miles deep, perhaps even supercritical water at its base where the line between liquid and gas blurs, all capped by a hydrogen-rich atmosphere. This atmosphere, while thick, might not be the impenetrable, crushing barrier we once thought. In fact, a hydrogen-rich atmosphere is actually more transparent than one like our own nitrogen-oxygen mix, potentially allowing surface-level water to receive enough stellar energy to remain liquid, even under a permanent global overcast. The implications for finding life are nothing short of revolutionary. If Hycean worlds are proven to be stable and common, they could vastly expand the number of potential abodes for life in our galaxy. Their larger size and thicker atmospheres make them far easier to study with telescopes like JWST than smaller, Earth-sized rocky planets. But the most astounding possibility is the form that life might take. We would be looking not for surface-dwelling, oxygen-breathing creatures, but for entirely different biochemistries. Life could exist floating in the planet-wide ocean, or it could be aerial, drifting in the temperate, hydrogen-rich skies, metabolizing chemicals we can barely imagine. The potential biosignatures we would search for would not be the oxygen and methane of Earth life, but molecules like dimethyl sulfide or chloromethane, which could be produced by microbial life in such an environment. Of course, this is a bold and speculative theory, and K2-18b is at the heart of the debate. Subsequent observations have suggested its atmosphere might also contain significant amounts of methane and ammonia, and the planet might experience intense internal heating from tidal forces, making its ocean more of a superheated, high-pressure stew than a placid sea. The recent, controversial, and as yet unconfirmed hints of dimethyl sulfide in its atmosphere only add to the fervor, as that is a molecule on Earth produced primarily by marine phytoplankton. Whether K2-18b is a true Hycean world, a hydrated mini-Neptune, or something else entirely remains one of the most pressing questions in exoplanet science. It forces us to abandon our Earth-centric search for life and consider that the universe, in its infinite creativity, may have devised ways to nurture biology in oceans suspended beneath the lightest of all gases, on worlds that look nothing like our own. Just 4.24 light-years away, a mere stone's throw in the vast cosmic ocean, orbits a world that holds a title of profound significance, our very nearest exoplanet neighbor. This is Proxima Centauri b, an Earth-sized planet circling the closest star to our own Sun, a discovery that instantly transformed our celestial backyard from a place of familiar planets into a frontier containing another world. Found in 2016, its existence sent a ripple of excitement through the world, not just because it was another rocky planet in the habitable zone, but because of its stunning proximity. If our interstellar ambitions ever become reality, this is the first port of call, the first stop on humanity's grand tour of the galaxy. But this neighbor lives in a notoriously difficult neighborhood. Proxima Centauri b orbits a red dwarf star, a class of star known for its tempestuous and violent nature. Proxima Centauri itself is a flare star, prone to sudden, massive eruptions that can unleash torrents of X-ray and ultraviolet radiation, blasting any nearby planets with energy that is hundreds of times more intense than what the Sun delivers to Earth. A single one of these superflares could potentially strip away a planet's atmosphere and sterilize its surface, scouring it clean of any delicate chemical building blocks of life. For a planet like Proxima b, which orbits 20 times closer to its star than Earth does to the Sun, these stellar tantrums are not an occasional inconvenience, they are a constant existential threat. This intimate orbit is a double-edged sword. It's the reason the planet resides in the habitable zone of its cool, dim star, completing a full revolution in just 11.2 Earth days. But it also almost certainly means the planet is tidally locked, much like our moon is to Earth. One hemisphere of Proxima b is forever bathed in the dull red light of its sun, while the other is locked in perpetual frozen darkness. This creates a world of extreme opposites, a scorching dayside where water would instantly boil away, and a frigid nightside where any atmosphere would freeze solid into a global ice sheet. For decades, this configuration was considered a death sentence for habitability, limiting any potential for life to a narrow, precarious sliver of twilight at the terminator line between the two extremes. Yet, nature is incredibly inventive, and new models suggest this story might not be so simple. The key to Proxima b's potential survival hinges on one great unknown: does it have an atmosphere? If the planet managed to form with or retain a sufficiently thick atmosphere over billions of years, that blanket of gas could work wonders. It could act as a global heating system, circulating warmth from the dayside to the nightside through powerful winds, dramatically expanding the region of temperate climate far beyond that thin twilight strip. A robust atmosphere could also provide a shield, deflecting and absorbing much of the harmful radiation from its flaring star. There's even a possibility that Proxima b possesses a strong magnetic field, generated by a molten core, which would offer a second layer of defense, helping to protect its atmosphere from being eroded away by the stellar wind. This leads to the most captivating question of all. Could there be liquid water on its surface? The answer is a tantalizing maybe. If the planet has that protective atmosphere and efficient heat distribution, large bodies of liquid water could theoretically exist on the dayside, or perhaps even a global ocean if the planet is a water world. Some climate models suggest that even under tidal locking, a planet with an Earth-like atmosphere could maintain open water on its star-facing side. The conditions would be utterly alien, a shallow sea under a dull red sun, with the potential for constant hurricane-force winds raging from the hot side to the cold side. It would be a harsh environment, but not necessarily an uninhabitable one. Life on Earth thrives in the most extreme conditions, from boiling hydrothermal vents to acidic hot springs, proving that biology is tenacious. If life could arise on Proxima b, it would have to be equally resilient, perhaps existing in subsurface oceans protected from the radiation, or in the planet's deep sea. Proxima Centauri b is therefore a world of stunning paradox. It is both the most accessible Earth-like planet we know of, and one of the most challenging environments we can imagine. It represents our best and closest chance to one day search for signs of life beyond our solar system, a prime target for the next generation of giant telescopes that will attempt to probe its atmosphere for the chemical fingerprints of biological activity. It is a constant reminder that the universe places its most valuable treasures right next door, but often guards them with formidable and awe-inspiring challenges. As we leave behind our nearest stellar neighbor, we arrive at a destination that redefines the very meaning of a planetary system, a place so densely packed with Earth-sized worlds it feels less like a star system and more like a cosmic archipelago. 40 light-years away, in the constellation Aquarius, the ultra-cool red dwarf star TRAPPIST-1 hosts a family of 7 rocky planets, each one a world of profound mystery and possibility. This isn't just a star with a few planets, it's a miniature solar system, a complete laboratory for comparative planetology, and arguably the single most important system we have yet discovered in the search for life beyond our sun. The architecture of this system is its first and most breathtaking marvel. All 7 planets orbit closer to their star than Mercury does to our sun, yet because TRAPPIST-1 is so incredibly small and cool, it's only slightly larger than Jupiter and emits a faint, dim red glow. This tight configuration places 3 of them squarely within the star's habitable zone. Their years are measured in mere Earth days, with the innermost world completing an orbit in just 1.5 days and the outermost in about 19. The orbits themselves are not just close to the star, they are remarkably close to each other. If you were standing on the surface of one of these worlds, the other planets would not be distant points of light. They would be prominent features in the sky, appearing as large as our own moon or even larger, with their geological features and cloud patterns clearly visible to the naked eye. You could watch your neighboring world rise and set, a breathtaking celestial dance happening in your sky every few days. This proximity is a double-edged sword for the potential of these worlds. On one hand, the planets are almost certainly tidally locked, meaning each has a permanent day side bathed in the star's dull red light and a permanent night side plunged into deep, unimaginable cold. This was once thought to be a major obstacle for life, creating a world of extreme temperatures. However, new climate models suggest a tantalizing alternative. If any of these planets possess a substantial Earth-like atmosphere, it could efficiently circulate heat from the scorching day side to the frozen night side, potentially creating a wide band of temperate, habitable conditions around the entire planet, not just a narrow twilight strip. The close orbits also mean the planets likely exert subtle gravitational influences on each other, a process that could generate internal heat through tidal friction, warming their interiors and potentially driving volcanic activity or even sustaining subsurface oceans beneath a frozen crust, much like Jupiter's moon Europa. The true revolutionary potential of the TRAPPIST-1 system, however, lies in its gift to astronomers, because the planets transit their star so frequently and because the star itself is so small and dim. The act of studying their atmospheres becomes not just possible, but profoundly easier than with almost any other system. When a planet transits a dim star, the dip in light is more pronounced. More importantly, when starlight filters through a planet's atmosphere during these transits, the chemical signatures imprinted on that light are far stronger and easier to detect against the faint backdrop of the cool dwarf. This makes the TRAPPIST-1 system the perfect natural laboratory for the James Webb Space Telescope. Webb is not just looking for one atmosphere, it is undertaking a systematic census, analyzing and comparing the atmospheres of all 7 worlds one after the other. This comparative approach is what makes the discovery so powerful. We can move from asking, does this one planet have an atmosphere, to asking fundamental questions about planetary evolution. Why does one world have a thick, Venus-like atmosphere of carbon dioxide while another has a thin, Mars-like envelope? Why does one show signs of water vapor and another appear bone dry? By studying these 7 siblings that formed from the same material around the same star at roughly the same time, we can finally understand the processes that make some worlds into vibrant Earths and others into barren wastelands. The TRAPPIST-1 system is a gift, a cosmic experiment played out on a grand scale, offering us a front-row seat to the story of how planets live and die, and whether the conditions for life are a rare fluke or a common feature of our astonishing universe. From the glass-stormed skies of HD 189,733b to the incandescent iron rains of WASP 76b, from the glittering diamond heart of 55 Cancri E to the frozen, ancient silence of Ogle 2005 Bilgi 390 LB, our tour of these 25 alien worlds reveals a cosmos of staggering creativity. We have witnessed planets being devoured by their stars, others holding onto oceans deep enough to drown solar systems, and some that shouldn't even exist, naked cores like TOI 849b and zombie worlds orbiting stellar graves. Each one of these bizarre discoveries is far more than a mere celestial curiosity. It is a vital data point, a puzzle piece forcing us to redraw our models of how planetary systems are born, evolve, and die. These worlds teach us that our own solar system, with its well-behaved planets in neat, circular orbits, might be the exception rather than the rule. The universe seems to prefer chaos, extremes, and violent beauty. The existence of a Hycean world like K218b dares us to imagine life flourishing not on a rocky twin of Earth, but in a global ocean beneath a hydrogen sky. The tight, resonant dance of the TRAPPIST-1 siblings shows us that solar systems can be arranged in architectures we never dreamed possible, offering not one but multiple chances for life around a single, faint star. Every strange atmosphere analyzed, every bizarre orbit mapped, pushes the boundaries of what we believe is possible, turning science fiction into scientific fact and reminding us that the only limit to planetary diversity is the limit of our own imagination. As our telescopes grow more powerful and our methods more refined, we stand on the brink of discoveries that will make these worlds seem almost ordinary. What will we find next? A planet with a ring system so vast it casts a visible shadow across its star. A world with seasons dictated not by axial tilt, but by a wildly eccentric orbit that brings glaciers and deserts in regular, apocalyptic cycles. Perhaps we will find the ultimate prize, the faint, telltale signature of biology in the atmosphere of a distant world, answering the ancient question of whether we are alone in this magnificent, bewildering universe. The journey of exploration has just begun. Each of these 25 planets is a doorway, and we have only just stepped across the threshold, so we turn the question over to you. Which of these strange new worlds captured your imagination the most? Was it the eternal diamond showers, the promise of a hidden ocean on a red dwarf world, or the terrifying beauty of a planet slowly evaporating into the void? Share your favorite in the comments below. We can't wait to see which marvel of the cosmos calls to you.